Let's look at 2.2a, exploring density curves. Think about each of the experiments Mr. McBurney could have students do. Predict or sketch what the histogram of the data might look like after many trials. For each case, identify which comparison about the mean and median you think would be true. So our first experiment is rolling a die and recording the value it lands on. So let's think about a die. A die is six-sided, and each outcome is the same, right? A fair die. So to the right, there is this histogram that shows the data from the experiment. Why does it make sense that the histogram would look like this? So look at each one. So this is our experimental. So if you think back to earlier math courses that you've taken, we've also been taught about theoretical probability. So theoretical probability is going to look like this. 1, 2, 3, 4, 5, 6, where you have six boxes or parts of the histogram. So the first one's 1, 2, 3, and all the way to 6. And what's true about the theoretical probability about each side of the die? They all have the same probability. So this histogram that we have in blue, it's really close to the theoretical that I drew in red. So it looks like that because each outcome is equally likely. Okay. How will the mean compare to the median? So the mean and the median, it should be about the same because it's uniform. Approximately the same. Because this is called a uniform distribution. Ran out of space. What proportion of the time do you think someone would get a 1 or a 2? So 1 or a 2? Well, it'd be 2 out of the 6, which is 1/3, which is 0.3 repeating, which if we were to write that as a percent, we'd get 33.3%. What proportion of time do you think someone would get a 1, 2, 3, 4, 5, or 6? That's all the outcomes. So that's 100%, 6 out of 6. Okay, experiment 2. Try to toss a penny, add a penny, and make it land on a target on the floor. So let's say the target on the floor is a penny. You're trying to land the penny on that penny. That's the target. So we're just going to do the prediction here and then we'll talk about it. So let's say the distance from the penny to the target and to the nearest centimeter. So 0 would be right on target. And then let's say you count their centimeters. Let's say this is 5 centimeters. This is 10 centimeters away. So this is really far away. This is super off target. So majority of them will be around 0, but it'll kind of taper off when you get further away. So this would be right skewed. And so whenever we do skewed graphs, think about mean chases the tail, right? So the mean would be over here, and then the median would be about here. So mean chases the tail is a great explanation, but you have to know the reason why. The mean chases the tail because it is not resistant to outliers. If you have outliers that are, let's say, around 10, that's going to make your mean get closer to that. So it's going to increase your mean. So the mean is greater than the median. Okay, we're just going to do the prediction and write on that instead of the actual. Okay, experiment 3. Try to stop a stopwatch at exactly 5 seconds. The number on the stopwatch is recorded. So we have 0, that's when you start it, and we have 5, and then let's say 10. So there's all the numbers between it. So whenever you try to stop your stopwatch, you're not going to have very many at 0 because you just started it. You're going to have the most around 5. So it's going to look like this. So what does this look like? It's symmetric. So when we have a symmetric graph, the mean and the median are approximately the same. Okay, so what we need to take from this is these density functions are also called probability distributions. We're going to see these a lot. These consist of all the probabilities of an experiment and how often they occur. And how often they occur. And when we add up all the probabilities, we should get 1, just like the dice example. All the probabilities together gives us 100%. So the area under the curve is 1 because it represents that probability distribution. So if you're in calculus, you learn to find the area under the curve by taking the integral. Well, we're in statistics, and we are going to use other tools to find the area under the curve for probability. We don't have to do calculus for this class, but that is where it came from, area under the curve. Okay, so let's look at our empirical rule. So the empirical rule is one of the tools that we can use to find the area under the curve. So we're going to look at the example of IQ scores. IQ scores are commonly thought to be normally distributed with a mean of 100 and standard deviation of 15. So mean and sigma, standard deviation, mu and sigma. Okay, so right there on that red line for this normal distribution is the mean, and then we go up by 15 for our standard deviation. So this is our 1 standard deviation, so it's mu plus 1 is that 115, and then this one is mu plus 2 standard deviations, and then this one is mu plus 3 standard deviations. And then you can go backwards, so this one would be mu minus 1 standard deviation. This one is mu minus 2 standard deviations, and then this one is mu minus 3 standard deviations. So if you were to take a random sample of people and find their IQ scores, then you would find that 60% of that sample is within 1 standard deviation of the mean. 1 SD of the mean. And then if we were to go 2 standard deviations, so that brings us to an IQ score of 70 and 130, then we would be 95%, then we would find 95% of the data. So this is 2 standard deviations. And then 99.7 of the data is within 3 standard deviations. So the way that this rule came about is that a group of mathematicians found data and kept on doing it over and over and over and over again. And they found that this was always true. 68% of the data is within 1 standard deviation, 95% is within 2, and then 99.7 is within 3. So because it happened over and over and over again, it became a rule, and a rule that we can use. So let's look at our questions. What percentage of the data is within 2 standard deviations of the mean? So for all 6 problems, we are going to draw what this curve looks like, and then what area are we looking for, okay? So it says within 2 standard deviations. So here's our mean, here's 1 standard deviation, here's 2. So this would be, I'm just going to put mean, and then we have 1, 2 standard deviations. So within means this area under the curve. So I would do, isn't it just this one? So it is what percentage of the data? 95% is within 2 standard deviations of the mean. Okay, what percentage of the data is further than 2 standard deviations from the mean? Well, let's draw it again. Here's the mean. 1 standard deviation is 2, -1, -2, is further than. So it's going to be the tail. You're going to shade the 2 tails. So isn't it just the opposite of number 1? So you would take 1 and subtract the 95.95, we get 0.05, which is 5%. Okay, before we go on to the next one, let's look at this model right here. So 1 standard deviation, we're going to find what each one of these bars represents. So this is mean. So remember that whole thing is this whole thing. Sorry, moved it. This whole thing is 68%. So in order to find out what this side is and what this side is, you would take 68 and divide by 2. So this is 34% and this is 34%. Okay, let's go further out. Let's find out what this is and this is. So we know 95% is the 2 standard deviations, but we've already accounted for 68% of them. So we find that, but then we got to divide it by 2 because you're going to the 2 tails. So that is 13.5%. Okay, and we need to find the next one, the 2 standard deviation to 3. So we know all the way out to the 3 standard deviations is 99.7. So we need to subtract the 95 and then divide by 2. And that is, I'm going to put a little arrow, 2.35%. Okay. And then our last little bit is 3 standard deviations all the way to the tail. So that would be the 100% minus 99.7 divided by 2. So that comes out to 0.15%. Very, very small. Guess we could put a 0 there. Okay, so now that we have that model filled in, we can answer these other questions. So it says, what percentage of the data is greater than 1 standard deviation above the mean? So let's draw our curve. So here's our mean. Is greater than 1 standard deviation. So here is 1 standard deviation. So we want to shade greater. So we've got to be able to find that shaded region. Okay, so there's more than one way to do it. But what I would think about is what is from the mean to the end of the tail? That would be at 50%. And what is just this part? That's at 34%. So we could subtract those and we get 16%. So 16% of the data is in the 1 standard deviation above the mean. Okay, let's look at the next one. What percentage of the data is between z equals -1 and z equals 2? Mu. Well, mu is 0, remember that? And so this would be -1, this would be 1, this would be 2. So between the two. So we're going to draw our lines and we want to shade it. So more than one way to do this, but I would think about like just here to here is a 68. And then I know from here to here is 13.5. So we could just add those up. We get 81.5%. Number 5, you take an IQ test and get a score of 130. Assume IQ is normally distributed with a mean of 100 points and a standard deviation of 15. What percentile are you? Okay, so let's look. So we're at 100. Standard deviation is 15. So this would be 115. This would be 130. So remember with percentile, it's at or below. So I would shade at 130 and below. So now we'll use the rule. So we know that this is 50, right? What is this? 34? And then this is 13.5. So we could add all those up. You get 97.5%. Okay, number 6. What score would you have to earn on an IQ test to be at least the 84th percentile? Oh, by the way, don't put percent. We need to say 97.5. So like 98th percentile. Okay, just need to fix that real quick. Here we go. So we know that an IQ score of 100 is the mean. And we want the 84th percentile. So we want the area under the curve to be 0.85 or 85%. So we know it's going to have to be more than 100. So let's just think about this because you want to know what this is. That's a question mark. So you know that's 50. So how much more in order to get to 84%? That's 34%. So didn't we just learn that that is one standard deviation? So that's 115. So it'd have to be a score of 115 is at the 84th percentile. Okay, let's go to the next page. Density curves and normal distribution. So let's go over the concepts. So for a density curve, the total area under the curve is our probability, which is 1. A uniform or flat distribution is going to look like this. Let's count out 5. 1. Let's try to make that straighter. 1, 2, 3, 4, 5. Okay, there we go. So we have 5 sections. The area is going to be 1. So we need to talk about the height. So if area equals 1, and there are 5 here. So area, think about area, length times width. So this would have to be 1/5, which means each outcome is equally likely because it's uniform, which each has the likelihood of 1/5. Okay. So let's look at mean versus median. So right skewed. The median, so the mean is going to be on the tail. The median is going to be right in the middle. So the median is going to be less than the mean. Okay, left skewed. The mean is going to be over here. The median is going to be here. So the median is greater than the mean. Symmetric, they're approximately equal. We can use this empirical rule, 68, 95, 99.7, to help us find the area of the curve and the likelihood of the data being between two values. So we will label the ideal mean is mu, and we can change it to be 0. And the ideal standard deviation is sigma. We can change that to be 1. And that's how we get our z-scores, which we're going to talk more about later. All right, so we are going to need to finish the application problems. I'm going to give you time to work on that.